Hey guys, Adam here with yet another episode of Ask Adam, where I basically just go through my weekly email and answer any arcade repair related questions or general electronics related questions you guys may have, mostly arcade repair related these days. But if you have a question and you would like me to take a look at it, can't promise that I'll be able to get to it, but send it to askadam@onecircuit.com, and who knows, maybe I will be able to answer it in this video or the next video, I guess, right? Anyway, let's dive into this week's email, and here we go. All right, our first question comes to us from Happy Adam, and it's a YouTube comment on my video on logic gates. Let's see. Wow, I ate this up. Watch, pause, take notes, play, rewind, take notes. It is awesome to finally understand what all these hieroglyphs are. One thing I don't understand is what's the point of a straight buffer? How is it any different than a copper wire? Also, I'm assuming a logic probe is hooked up to ground. I have never used one. So yes, a logic probe is hooked up to ground. It's hooked up to ground in 5 volts. And there's circuitry inside the probe that uses that to figure out what kind of a midpoint is, right? And so anything above that midpoint is considered a logical 1, and anything below that is considered logical 0. So your question is, what is the point of a straight buffer? How is that different than a copper wire? So if we draw a gate here, let's say we have an AND gate, and he is feeding, I don't know, a couple other gates. So he's going up and he's driving, let's say, an inverter, and then maybe he's driving another AND gate, and then maybe he's also driving, I don't know, an OR gate or something like that. We'll draw an OR gate, and so on. Each one of these gates inside has capacitance, and it's just by the nature of the way that these gates are made in silicon. So inside of these gates, on every pin, input pin, and actually output pin, has some capacitance to it, right? So if we look at how or what the signal would look like, let's say at this point here, it goes from a logical 0 to a 1, and it's a 1 for a while, and then it goes to a 0. Okay. What do we expect to see on this side, right? Same thing, yes and no. What you'll actually see is due to this capacitance, it'll be low, and then as soon as that changes, it'll start to climb to a logical 1, and it'll be a logical 1 for a while. And then once it drops, it'll ramp down. So it ramps up and it ramps down. That's actually the proper term there, ramp up and ramp down. And it's because of that capacitance, right? You got to charge that capacitance up to 5 volts, and then you got to discharge it back to ground. But it'll still work. I mean, logically, it still works. You've got this threshold. Actually, let me use a different marker here for that. So you've got this threshold here, right? We were just talking about that actually with the logic probe business. And anything above this threshold is a logical 1. Anything below is a logical 0. And so what actually happens is, as far as these gates are concerned, it doesn't see the signal as being a, this is not very dark. Let me try to use a black one. These gates don't consider this input to be a 1 until right here where it crosses that threshold. And it doesn't consider it to be a 0 until here where it crosses that threshold. So you can see it's kind of shifted a little bit, okay? And it's also maybe a little bit smaller. And so what happens is, as you increase this gate count, we've got 3 gates here. Let's say, for example, you had, I don't know, 50 or 100 of these gates here, okay? All that capacitance adds up. And what it does is it changes the look of this curve. So rather than being like this, it would take a much longer time for it to ramp up. And then likewise, when it hits here, it'd be a much longer time for it to ramp down. And what happens is your pulse here actually gets smaller and smaller, right? You can see, if we go to draw a little line here so we can line these up, it would look something like this. And then over here, and it's hard to tell, I'm probably not drawing it well enough, but what can actually happen is these pulse will shrink. Let's say you have 1,000 of these things, right? Well, this thing would look like this. It would take so long for it to ramp up that it wouldn't even cross the threshold. And then all of a sudden now you got to go down. Oh, okay, so I'm going down. And it wouldn't even cross that threshold. So in that case, it would just be nothing, right? So it wouldn't work at all. So this is called fan out. In this case here, this gate has a fan out of 3, right? And then once you start adding more, then it's got a fan out of 100 or whatever. So that's the problem. So how do we solve this problem? You solve it basically by breaking it up into smaller problems. So if we take this circuit here and we erase this business, actually let me just erase all this here because I'm probably going to need this real estate. And so if we take a buffer, right, and we stick a buffer here, well, now I can drive these 3 with a buffer. Now if I have a bunch more, that's fine. I can use another buffer. Maybe drive 3 more, and then another buffer, and drive 3 more, right? So each one of these buffers has a fan out of 3, 3, 3, 3, 3, 3, but you can use it to handle a situation where you have massive fan out. Let's say this is a reset signal to all the chips on your board. You got to reset them all from a single source. This is exactly what you would use buffers for. So buffers are typically used in that case to handle fan out issues, but they're also used, like I said in my previous video, where you want to turn a signal on and off and have a bunch of them hanging off of a single source. Like if you have a buffer that's got a tri-state enable. We talked about that, and I think I talked about that in my logic video. Tri-state basically just means it can be 0, 1, or completely disconnected. Like that's the third state, right? They call it a high impedance state, which basically means it's like a resistor of infinite resistance, right? What's infinite resistance? It's a wire that you've cut, and it's just completely, cut, severed. And so those are the 3 states. You can be logical high, logical 0, or just completely severed. And that's what a tri-state buffer is for. So it's different than a normal buffer, because normal buffers are always on. But in general, that's typically where you will see buffers in a situation where you've got to handle a massive fan-out situation, or situations where you want to turn signals on and off. Okay, our next question is from Brian Weiserick. Hello, Adam. Love the new format, and I'm very happy to see new videos. My question is about my logic probe. My probe has a switch for TTL CMOS and a connection for sync. Can you discuss how I would use these options for arcade and pinball repair? Can you discuss, I already read that. I also have a logic analyzer, and I love to see an in-depth video on how to use it to its fullest. Thanks, Brian. So yes, I do plan on doing a standalone video for the logic analyzer type stuff. There's a lot to cover, and I want to make sure I do that video justice, and so a little bit too much to get into here, but I do plan on doing one, so look for that soon. TTL versus CMOS on your logic probe. Yes, so TTL and CMOS are different types of chips, okay? So TTL stands for transistor logic, and CMOS stands for, I believe, complementary metal oxide semiconductor. So those chips, although they have the same function, right? The logic gates, let's take like an AND gate, for example. You can have an AND gate that is a TTL AND gate versus a CMOS AND gate. They both perform the same exact function, but inside physically, the way in which those chips were made, the process in which those chips were made is very different, and they can have different characteristics. And so hopefully that kind of explains just the difference between those two groups of chips. Arcade games are primarily all TTL. I don't know too many arcade games, if any, that use CMOS. But basically, if you were going to debug a TTL part, then you would have the switch in TTL mode, and if you were debugging a CMOS part, you would have in CMOS mode. And the difference really from an outside perspective, like you've got this chip, and either it's branded, it's TTL or CMOS. From an outside perspective, what does that really mean? It really means on the voltage levels in which the part considers inside what is a logical high and 0. So if we look at this board, which I have kind of whipped up ahead of time here, I have TTL on this side, on the left side, and then CMOS on the right side. Now I know in the videos that I've done in the past, in all my explanations, I kind of oversimplified the way in which a logic probe works, and that it just basically has a single threshold and it looks at what is above and below. But internally in these chips, it's not that simple. There's kind of 2 ranges here. There's a high range and a low range. And so inside, when the chip sees a voltage that's within this range, it considers it a logic high. When it sees it down here, it considers it a logic low. This is kind of the danger zone, right? You don't want to be in there because bad things can happen from a chip perspective. But going back to this, the TTL spec, and I think this is accurate, I may be a little off, but the TTL spec, if you're anywhere between 0.8 volts and ground, that's considered a logical 0 or low. And if you're between 2 volts and 5 volts, that's considered a logical high, okay? If you look at the CMOS spec, it's a little bit different. It's kind of broken up into thirds here. Anything between 1.5 and ground is a logical 0, and anything between 3.5 and 5 volts is a logical high. So if you had your switch in the wrong mode, would it maybe give you an incorrect result? Maybe, I guess. It depends on the circuitry inside the logic probe. But in general, you really don't need to, at least in my experience, need to play around with these various modes, because either the board set that you're working on is either completely in TTL or it's completely in CMOS. And for the purpose of arcade games and pinball games, it's almost always, if not always, TTL. So I haven't really come across a case where I've needed to play around with CMOS. but hopefully this gives you a little bit of explanation as to what that switch is for and when you might need to use it. Your other question was in regards to sync, and so I think that is actually an external sync. And so if you are probing, let's say, the reset signal on your board, and you never expected it to toggle, right? Unless the watchdog went out and something very bad happened, you could hook up some piece of test equipment to that sync signal so that if at any time the reset did happen, it would fire a signal over to your other piece of test equipment and it would do whatever you want it to do. Let's say a logic analyzer would start grabbing information or something else. And so I believe that's what that's for. I believe it's an external sync for triggering other outside things. So hopefully that answers your question. All right, our next question is from Sean Ryder, looks like. Hi Adam, I have two games with somewhat similar issues. The problem is corruption on the backgrounds of the playfields in the form of vertical bars or lines. The first game is Cloak and Dagger, and on some screens there are broken vertical lines. The lines also flash on and off, and so I theorize that the video might be double buffered, which causes the lines to flash as the screen animation changes. Actually, arcade games are not double buffered. PC video hardware does use double buffering for animation and to prevent tearing and all sorts of stuff, but video arcade hardware doesn't use double buffering because it's just so costly. And so what happens is the video hardware, the memory is programmed, by the CPU. This is all the stuff I want you to draw, and then the beam starts, going across your monitor, drawing that image. And while it's doing that, it's telling the CPU to back off. Don't put anything into memory, anything new into memory, so you don't get tearing. We'll talk about that some other time. But it draws the entire image on the screen, and then during the horizontal blank period, where the beam goes all the way from one end of the monitor to the upper corner, or is it lower right corner to upper left corner, during that process, it sends a cue to the CPU saying, now's your chance, you better give me everything you can, because once I start drawing, you're done. And so during that process, or during that time rather, where the beam is moving in that diagonal direction to the upper left corner of the screen, CPU is refreshing the entire video RAM, what it wants to draw next. And then once it starts drawing, it again tells the CPU to back off, and it draws the screen. So while it's drawing the screen, the CPU is not sitting there idle. It's checking your joystick and your buttons and calculating where sprites are going to be moving, but it doesn't actually update any of that information in the video logic until that vertical refresh period. So anyway, so you have a problem with Cloak and Dagger, and some screens have broken lines. Game 2 is Bubbles. Its failure started as white vertical lines on the blue playfield, but then it progressed to the entire playfield being white instead of blue. So I'm guessing it's bad screen RAM for both games, but I am sure how to figure out where the screen RAM is by looking at the schematic. Can you offer any tips to figure out how to identify what RAM chips and the system is dedicated to video? So let's tackle this backwards. So your last question here is, can you offer any tips to help figure out how to identify what RAM chips in a system is dedicated to video? So let's talk about that. So almost all arcade game logic, video logic, is very, very similar. And so it starts at the very end where you send the RGB signals to the monitor. So let's just pick a color. Let's pick red, but I'll draw it in blue. So you have your R signal that gets sent to the monitor. Let me just make sure that you can all see this up here on the frame. Sorry, I had to adjust my camera there. So this red signal gets sent to the monitor, and it comes from a color prom, all right? And these color proms typically send or have 4 bits to them. So it sends a hex value, which is digital, but then it uses a bunch of resistors to turn that digital value into an analog value that gets sent over to the monitor. So this is a little DAC, a DAC, digital to analog converter. It's very simple logic, and they use resistors to do that. But anyway, this is your color prom, okay? And this is just the red color prom. Again, you'd have the same thing for green and blue, but we're just looking at red for now. And so there's an address that gets sent to this color prom to indicate what value of red I want to send to the monitor, okay? That value, or that address, comes from, or can come from, multiple sources depending on the hardware, the video hardware. And so like you've mentioned here, background, okay, there's background, there's sprites, there's maybe characters getting drawn on there. Anything that gets drawn onto the screen, okay, goes into this mux. And a mux is like a little traffic cop. It basically just switches up and down and lets each one of these guys have a turn going out. So maybe this is your background stuff, right? So we'll just call this back. Maybe this is sprite, SPR. And I don't know, maybe this is character, CHR, okay? And for each one of these, you've got certain things. We'll start with the background here. Okay, you've got a bunch of EEPROMs, right? And these hold all the background information. Background information is typically simple, so you probably won't have a lot of EEPROMs, but things like sprites, you might have a lot more EEPROMs, okay? So in here is the actual background tiles themselves, you know? Maybe it's a cloud, maybe it's rocks or whatever is in the, kind of in the background. So that's located in one or more EEPROMs, and that data is kind of all, you know, concatenated together and becomes part of that address. The other thing that becomes part of that address is your palette RAM. Okay, and so lots of times you can have inside of your color PROM, it's broken up into smaller groups. Okay, so rather than just have a huge list of, let's say, 200 entries, let's say, well, let's have 100 little 2-entry, you know, palettes inside of this thing. And so these are broken up into lots and lots of little palettes, and this guy will choose what palette you want to select, and so that gets factored into the address as well. So you've got ROM. You just draw that in so you can see ROM, a bunch of ROMs, and then you've got RAM, and this is the palette RAM. So I'll write that in here. Palette. Did I spell this right? Okay. So you got ROM and you got RAM that feeds into that. What dictates what you're drawing to the screen is actually in the video RAM. Okay. So you got video RAM. Now, depending on the architecture of the game, you may have one or more. Like the background logic may have its own background RAM, and maybe the sprite logic has its own. Actually, that's almost always how it is. The sprite logic has its own video RAM, and characters might have their own video RAM. So this is really just for background. Back. And so this generates an address for all these ROMs. So you can think of it this way. The RAM dictates, okay, the position of all the stuff that's going to be on the screen, as well as what it wants to draw on the screen. And then the ROM dictates what that's going to look like, okay? And so if I could, I'm tempted to leave this here, but I kind of have to erase. Well, maybe I can do it down here. So if you think of your screen, I'll draw it in red so it stands out more. If you think of your screen like this, here's your monitor, okay? And for the sake of argument, let's say that it's 64 pixels by 64 pixels, okay? Each background tile, each little character, whatever, is 8 by 8. We talked about that in the other video. And so if you break this thing up into 8 by 8, okay, and hopefully I can do this. Alrighty. If you break that up into little 8 by 8 blocks, all right, what's in this RAM is what the video hardware wants to put in each one of these little blocks, okay? So let's say that you were drawing, or let's say that this was Super Mario Brothers, okay? And you had a couple of different background tiles. One was your little brick that looks like this. And then one was, I don't know, a piece of pipe. You know, maybe it looked like this or something. And then one was a piece of a cloud, right? Maybe not the whole cloud, but maybe a piece of the cloud, okay? And this might be background tile number 0, and this might be background tile number 1, and this is number 2, okay? Inside of this video RAM are things like this, you know, 2, 2, 2, 2, because on the bottom where Mario is running, you've got all these little bricks, right? And then maybe in the sky, you've got 0. And then, I don't know, 7, 2, and 7, 2 are the other halves of this cloud, which I won't draw out. And then maybe there's a piece of pipe here, so it's 1, 1, and then you've got something else going on. But you can kind of see what's going on here. There is a lookup table, okay, inside of these guys that have this, okay? Location 0 in these ROMs is part of the cloud. Location 1 is part of the pipe. Location 2 is part of the bricks here. And then in the video RAM is what the screen looks like. It uses these little pieces like a puzzle, and it puts together the whole image for you, okay? And so when you draw the screen, it basically starts in the upper corner of this, and it just starts plowing through all this, okay? And then sends that information to the ROM, say this is what I want you to draw. Moves on to the color PROM, figures out what each pixel is and sends it off to the monitor. And so you're saying that you're having issues with white lines. So I don't think it has to do with this RAM here, because the job of this RAM is to just dictate what gets drawn on the screen, not how it looks. Does that make sense? How it looks is kind of determined over in this section of logic over here, right? The ROM logic definitely plays into how it looks, and then after that as well. And so I forgot to mention that there is also a serializer here, because the data that comes out, SER, the data that comes out of here is really a single line, like this single line here, and then the next line, or it's 8 bits, 8 bits, 8 bits. It kind of always does it in like little slices, boom, 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 boom. And so you're saying you're getting a white line, is that what it is? Vertical bar. So it could be this serializer. It could be that as it's drawing this image, every time it starts drawing the image or the tile or whatever, in location 0, like this little guy right here, there's something screwed up in the serializer, and it always sends out the wrong color value and ends up being white on your screen. Could be something like that. It could also be something with this palette. I mean, it depends on the nature of the bar. If the bar is really wide, then it could be something related to the palette. If it's like a single slice, a single pixel, that to me makes me think it has something to do with the serializer logic, or as the data flows into it. It really depends on, you know, like I said, the type of the artifact that you're seeing, whether it's skinny, whether it's wide, and those sort of things. But now that I've drawn this picture here, and I've kind of explained or put myself out there to say that almost all you know, arcade video logic is like this, let's take a look at some of these, like the Cloak and Dagger or maybe the Bubbles, and let's see if this theory holds true for some of those games. All right, so we have the Cloak and Dagger schematics that we found on the web. Oh, top secret. We'll risk it. Let's go down to schematic portion of our package. Okay, so what we're looking for is RGB out to the monitor, right? Because we're going to start at RGB, we're going to work our way back. Hopefully we'll find things like the DAC, what's after the DAC? The PROM, the MUX, serializer, ROM, and then the video RAM. And then hopefully we can figure out what might be causing your problem. Oh, right there. So here's our RGB. Why does it do that? And you can see here, so let's work our way back right here. So here's the resistors, and then this is a just a register. So this is the DAC. This is where we're converting that digital information into an analog signal. And so that feeds from this guy here, which is our color PROM. Although this is more like a dynamic color PROM. This is something that can be programmed and changed on the fly. You can see it's got a write enable here, so it's actually a piece of RAM as opposed to a ROM. But for our purposes, you can think of it as a color PROM. It's just that it can change. And so the address looks like color A0 to A5, color address 0 to 5. So we should see a MUX driving this that lets us select between background information, sprites, and all that good stuff. So let's see if we can find that color A0 to A5. Let's see. Ah, right here, video. Color A3, A0, all that good stuff. So these are MUXes. So you have 4 inputs, and then these 2 little bits here will select one of the 4. And so one of these must come from a background stuff, one must come from sprites and other thing. Let's pick the first one here, P-bit, 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 P-bit. So we're looking for a P-bit. This is motion object, so this is sprite, so I don't expect it to see it here unless P-bit is for sprites. But I did see M-bit, which makes me think it's not for that. Oh, this is P-bit stuff right here. Oh, playfield. Okay, so this is playfield. This is background. This is what we're looking for. So serializer. It looks like they're using a MUX as a serializer. You can see the data actually feeds in here, and then they choose between the bits by using these select signals here. Interesting. So just a side note, but you can see here, this signal here, cocktail, feeds into those selects and actually flips the select pattern. Can you think of why they would want to do that? It's because when you send the image to the screen, right, when you're drawing the little 8x8 tile, you draw it one way, but when you're in cocktail mode and the game flips, you're actually going to draw it in reverse, right, because the entire image is kind of reversed. So that's why that's in there. So you have the serializers here, and then here you have the ROMs. And so these hold all the little background tiles. And then what should be driving the ROM is the RAM, some sort of video RAM, PFD PFD I don't see on this sheet anymore. We scroll up here, sync chain, right here. So this is the working RAM, playfield RAM, PFD. So there you go. So RAM feeds into ROM, feeds into serializers, feeds into MUX, so on and so forth. So if I had to make a guess, educated guess as to what might be causing that issue, again, it depends on the nature of the white line. I would suspect it might have something to do with this logic right here, whether it's a ROM issue, especially if it comes and goes. I think these guys here, if it were me, these probably would be the first ones that I would take a look at. Looks like there's some additional muxing over here. So anything is fair game in this area. You know, these guys here, or these guys right here, I probably would start with maybe some of those guys right there. Of course, I'm pointing to the screen. You can't see my finger, but anyway. So yeah, so in answer to your question, that's probably the area that I would take a look at. Maybe replace a couple of components in this area, and then see how it goes. Okay, our next one is from, looks like Robert McKilwee, and he asks, Adam, I really enjoyed your new video, Ask Adam #1. I am new to this, and a lot of it is over my head, but I did learn a lot. I have a Gunsmoke PCB with a graphics glitch. The problem is that there are no schematics for Gunsmoke, at least none that I have found, and the traces are internal. Where should I look to find what is causing the problem? What the game looks like, okay, so he has a picture here, so I'll throw it up so you guys can see it. What the game looks like, note that the building is supposed to be on the right side of the screen is repeated 4 times. Someone suggested looking at the MAME source code to find out where the background ROMs were, and maybe replacing the RAM associated with them. I included the MAME source code below, but since I could not follow the traces from the GS14 ROM, okay, we'll get to that in a second, I replaced 13 of the 74LS273 chips. But of course, this shotgun fix did not work. Any ideas on what to try? So actually, luckily, we still have this drawing that I just whipped up for the other question that I answered, and it talks about the background logic, right? That draws the background for the scene. So it looks like in your case, rather than have a RAM, you actually have a ROM. You have this GS14 ROM, and in your case, well, let's take a step back. So in other games, right? The CPU will kind of draw the screen. It'll fill this little what do you want to call it, tile map with pointers that are going to point into the tile ROMs, and then those get drawn to the screen. But in your case, it looks like you have a ROM here and not a RAM, and that's okay. So it looks like the game developers basically just designed a level and they burned it into that ROM, and you always do the same level, right? Or maybe it scrolls or whatever. But rather than the CPU dynamically changing the level on the fly, it's been pre-programmed into a ROM. But the hardware works the same way, right? Whether it's a RAM or a ROM, it works the same way. Let's assume it's a RAM though, because I think other people might have similar problem as you, where they see artifacts of the screen that are being drawn 4 times, 2 times, 8 times, whatever. So in most cases, you might have a RAM here, and you'd have a MUX on this end of the RAM. And you'd have 2 things that would be able to address this RAM, one of which is the CPU. So if you remember, we talked about a little while ago about the beam, and it's drawing the screen here, and when it gets to the lower right corner, it stops drawing and it works its way up to the upper left corner, it sends a cue, right, a V blank, a signal over to the CPU saying, now's your chance, you can start filling this with new information. So at that point, the CPU is doing just that. It's writing into the RAM, and it's drawing the next frame. Once that beam reaches the upper left corner, the CPU is told to back off, and you have something else addressing the video RAM, right? And that is your horizontal and vertical address counters. So we'll just write that there. Horizontal and vertical address counters. And that makes sense, right? Because now that we're drawing the screen, we're going to let the horizontal and vertical address counters, which tell us where the beam is at any moment in time, we're going to let that generate an address, right? Which basically points into our little tile map here. We start over here, we get to the end, we roll over and draw the next line and the next line, and so on and so forth. So you're seeing something being drawn multiple times, okay? Well, on our little example here, we have an 8x8 tile map, right? So this goes 0, 1, 2, up to 7. And 0, 1, 2, 1, 2, 7. And so what I've done here is I've just kind of drawn out what that looks like in decimal and what that looks like in binary, okay? Now you'll hear me talk about in my other videos significant, most significant bit, least significant bit. And what I mean by that is when I say something is most significant, it has the most effect on the value. Okay, so if I point to this guy over here on the left, that is the most significant bit. Okay, when I change or when I mess with that bit, it's going to have the biggest impact on the overall value, right? You can see here that it's a 0, and then once you switch to a 1, you've just moved to the next group of 4. Okay, if you look at this bit, for example, it's a 0. When I change it from a 0 to a 1 and 0 to 1, I'm really just jumping in groups of 2. But this guy here, when you change it, it jumps in groups of 4. Okay, so it has a bigger impact. It has a bigger significance on the overall value. Okay, so the most significant bit is always all the way. Which way am I pointing? I should point this way, right? Because the camera is reversed. It's always on the left, and the least significant bit is always on the right. Okay, because it has the smallest impact. So what happens if we start messing with these bits, all right? Up here we have our vertical and horizontal address counters, and it's driving this value. We assume it is, right? We assume the value that's driving is correct. 0, 1, 2, 3, 4, 5, 6, 7. Let's just focus on the horizontal part, right? 0, 1, 2, 3, 4, 5, 6, 7, and it does that over and over and over. Let's say that there's something bad going on. Where's my red marker? We'll use red for bad. Let's say there's something bad going on right here that forces one of those bits to be 0. What's the effect? Let's say I mess with the most significant bit, and I drive it 0 all the time. Well, these numbers don't change, right? It's already 0. But over here, we would change to 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. So what are those values? Well, they're the same values that are right here. So now we've got 0, 1, 2, and 3. So the horizontal portion of this counter is going 0, 1, 2, 3, 4, 5, 6, 7. But what does the RAM see? It sees 0, 1, 2, 3, 0, 1, 2, 3. Okay? So even though the beam is physically over here, the address that's getting sent here is back in this area. So whatever is in this portion of the tile map is going to get drawn twice. Okay? Now that's not exactly what you're seeing, but let's take it a one step further and let's see what happens if we mess with now this bit. Okay? If we mess with that bit, where's my eraser? Let's erase this. So I mess with both bits. So let's say I drive them to 0. Well, then we get 0, 0, 0, 0, 0, 1, 0, 0, 0. We're forcing that bit low. Same with this one here. We just keep going. 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. So we've drawn 0, 1, then we draw it again, 0, 1, 0, 1, 0, 1, right? We've just drawn the same thing 4 times, right? And so I think that if you were to look at some of the bits on that address, you'll see a few that are stuck. They could be stuck low, they could be stuck high, but they're probably stuck all the time. The horizontal and vertical address counters are trying to address the ROM properly. There's something in the way that is screwing that up. You have no schematics. That is the absolute worst situation to be in, and so I can sympathize with you. So what I would say is start with that ROM, this GS14 ROM. Take a look at the address bits. Chances are you're going to find some that are tied low all the time, tied high all the time. You say it's in the upper portion of the screen. I guess it doesn't really matter, but probe around and see that. Check those address lines. I suspect you're going to find some that are just stuck all the time. All right, I think we have time for maybe one more. This is getting a little long, but let's see if we can find a short one here. All right, how about this one? Dathan Walters, he has a question on logic adder chips in an arcade game. Hi, Adam. What are logic adder chips used for in arcade games? I know logic adder chips add 2 binary bits together, and they get the sum and the carry. But what are they used for in arcade games? Is it used for vector display games only? So no, actually, adders are used in, I want to say, all arcade games for movement. And so if we go back to our little drawing here, remember we talked about the tile map, and let's assume that this is actually not a tile map. Let's say it's a sprite map. They both work the same way. You have memory that tells you where all the tiles are and how you want the scene to look, and you also have memory that does the same thing for sprites, right? We talked about that a little bit. So over here, let us draw another square. And let's say that this actually represents what is going to be drawn on the screen. So this is what our memory looks like. It's a representation of what's going to be on the screen. This is actually what's going to be on the screen. Okay. Adders are usually located right here between the horizontal and vertical address counters. Let me use a different color here. I'll just put in, say, green or something. We'll do this. Actually, that's a horrible color. You can't see that at all. I'm using black. Get rid of this. And hopefully you can see it. Yeah, it's much better. We'll do a plus and a minus, right? Because it can do maybe positive or negative numbers. That's typically where you're going to find your adder, okay? And here's why. Let's see what's going on here. So let's say inside of this memory, we have a guy. Let's say this is punch out. Let me draw my guy here. Look at that. How's that, huh? Beautiful. There's our boxer. And let's say that this value is a 0. So the horizontal and vertical address counters are telling you where the beam is, and we're not doing anything to it. We're adding 0 to it. That means that value, those values, those counters are being used to generate an address to look up where you are in the video RAM, right? So if this is 0, then we have a 1-to-1 correlation between where the beam is on the actual screen and where this logic thinks the beam is, okay? So we start in these upper corners and we draw the scene, right? What's going to look like over here? It's going to look like this. Our little dude looks like this, right? Okay. Now let's put a value in here. Let's say 10. Okay. So the beam is here at location 0. What does the logic think the beam is? The logic thinks the beam is at location 10. So it's got a head start on where the beam is. All right. So the beam is actually here. This guy thinks we're over in here. As we start drawing our scene, boom, I reach this area and I start drawing my guy. I'll draw him in a different color here. You see how that works? That's not good at all. He's totally disproportional to the first picture that I just drew. I apologize. How's that? A little better? All right. But you get my point, right? As this number increases, this guy gets more and more of a head start. And so he thinks that, you know, we're further along than we really are, all right? So if this is an even larger value, this would be over here, okay? So let's finish this example, let's put a negative value here. Let's say negative 10. And you can already guess what's going to happen here. The beam is actually physically here. This guy thinks the beam is not even started yet, okay? So we start moving along, moving along. Finally, we get to this area. Okay, I think the beam is 0, right? Actually, so we're at location 10. We subtract 10. This guy thinks we're at location 0, when really we're at 10. Then we start drawing, and then we get to the guy right around here. Okay, so in this example, he's over here. All right, draw him out like that, blah, blah, blah. So positive values are going to send your guy over in this direction. Negative values are going to send your guy in this direction. This is usually called a horizontal position register, okay? So every sprite in your game has a horizontal position, and the CPU, right, is going to write this when, we talked about this, you know, already, but when that beam is drawn up there, not only does it fill this with new information, it updates these registers that let you know where the sprite's positions are. Pole position has this, punch out has this. I can probably show you actually real quick where these are in punch out. But all your sprites, the way in which they move is through logic like this. You know, you have horizontal and vertical depending on the nature of the game. Horizontal and vertical position registers, and by mucking around with those, you can get the sprites to move in space. Let me just pop open real quick. Don't want to take too long on this, but let me pop open the punch out video schematics, and I'll show you exactly where those are for the opponent as well as your player. Okay, so here are your schematics for punch out the video PCB. And this whole upper section here is for your opponents. So Glass Joe, Bald Bull, etc., all those guys. So let's see if we can find the horizontal and vertical position registers and adders. So the data comes in, and it looks like it gets registered right here. That's the wrong guy. Right here, you can see we have HS, a couple registers here that hold a horizontal value, HS, and then down here, VS. And those, like HS, for example, pours into these adders. So this is 74F283 adder. It takes in an A value, a B value, it adds them together, and it spits out a sum, and then there's a carry. And so you can kind of daisy chain these all together so that you can add larger values. Each one of these is a 4-bit adder, but if you chain them all together, you can get 8-bit adders, 12-bit adders, and that's what they're kind of doing here. So that's it. So these are your horizontal position registers, and then those values get updated by the CPU, right, as the game is playing, and then they get added to the horizontal and vertical position counters, and that influences where the character is, Glass Joe and those guys. Now let's see if we can find the same thing or something comparable for you, the Challenger. And the Challenger logic is all down here on the bottom. And it looks like, okay, so it looks like there aren't adders for you. Looks like the values get loaded up in here, and then they kind of just get used to generate an address. I'm not seeing any adders here that flow through. There's your RAM and so on and so forth. So that, I guess that kind of makes sense. I don't think that when you move your character in the game, I don't think that he stays the same shape and moves, right? If you look at Glass Joe and some of those other guys, they can have the same shape, especially when the match starts, right? Glass Joe's in the upper corner, and you hear the song do 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 do, and then he kind of marches back and forth, and he gets bigger. We can talk about that some other time, how that effect is done. He gets bigger, but he also moves in the center of the screen, right? Where you change your body position, right, as you're moving left and right. So it's not really physically the same sprites are being used, redrawn in different positions of the screen. It's actually a different set of sprites, and so I think that's why. Am I accurately representing what you're doing? So I think that's why there's no horizontal and vertical position counters in this logic for the player, but they are there for the what is it? The opponent, and they're there in a ton of other games. Just look through, and you'll probably find them in games like Pole Position and Pac-Man and etc. Well, I think it's going to do it for this episode, guys. Sorry I went a little longer than I expected, but hopefully there's a lot of good stuff in there for you to kind of process and go over, and hopefully you found it interesting. So if you guys have questions for me, just go ahead and email them to askadam@onecircuit.com, and who knows, maybe I'll have time this week to answer them. Depends on my work schedule and whatnot, but we'll see how it goes. So, alrighty, that's going to do it for me. So God bless you guys, and we'll catch you on the next one. Hey guys, Adam here with yet another edition of Ask Adam. No, not edition, episode. Another edition of Ask Adam. Logic Probe video. Wow. Oh, did I say the guy's name? Oh, I forgot to turn this on. Okay, our next question is actually the first that I got. Went a little bit longer than expected, but hopefully you found all this. Hopefully. Well, I think this is gonna do it. Blah blah blah. Why did I end up over there on this monitor? Hopefully it'll keep you guys interested in something, whatever.